So there, I'm recording it. Okay, so if you go to and open up, let's find the ISA format. There it is. Okay, so in the ISA format, which we use for binary, but since the assembly instructions are the same as the binary ones, the assembly instructions are just codes for these, just like it's like a symbolic format for instructions, but you still have to understand what they do. And so here's the names, the assembly names of the trap routines. Whereas before you were using like trap x20, x21, x22. Now you can use get C, out, put S, and halt. Okay, but here's the actions. This was like on the last demonstration. These were the form of the answers I wanted for the some of those one of those first problems. But let's look at this segment of instructions that are labeled code organization support. Now there's 3 of them at the beginning that all are very similar. And then there's a partner to that, RET. We don't use RTI, so just ignore that. So trap, JSR, and JSR are all support subroutines. Now trap reports a special subroutine in the system space. So that's what each of these does. The first thing it does. So each of these instructions resides at a certain address in your program. That address, when this thing is run, is the PC counter. So that these 3 sort of work like branch. You know, branch puts, like you can see, JSR has a PC equals PC plus 1 plus PC offset 9. So the branch, jumps somewhere. It changes the flow of which instructions are next, and so does JSR. But it does something that branch doesn't do. For all 3 of these instructions, they first write something to R7. PC plus 1, PC plus 1, PC plus 1. Well, this is the next instruction after the trap or after the JSR or after the JSRR. So this is the same for all 3 of them. And that's where this last one comes in, RET. So after you save the old PC counter, you're going to set the PC counter to a new one where you jump automatically. There's no condition. You jump somewhere, either to a specific space low address in system space, to the PC counter in the program, or you have a base register where you put the address into the program and loaded it via LEA, say. And then after so you jump to this other place, whatever the PC counter is, you run your subroutine. At the end of your subroutine, you have the call RET. Well, your subroutine will usually not change R7. So then when you come back, when you put R7 into PC, what you're getting is the old PC counter right before you called trap JSR plus 1, the next one, and so it jumps back there. Okay, so let me just diagram how this works. So you have your main. This is about sub routines. And these are important because assembly subroutines are the foundation for C and Java functions. And in Java, they're called methods. As we'll see, Java is a set of class definitions, and each class definition has in it, apart from some field variables, little tasks that you can accomplish, and they're called methods, ways of doing things with data. Well, functions in C look exactly like methods. These are the same things, except C doesn't have classes and objects. But when these are translated to assembly language, they're translated to subroutines. So subroutines are the assembly foundation for functions and methods. So we get to see, we're going to be, you will understand more. We have to understand how subroutines work and what's going on. So you have some, say main, program, driver, some kind of main code. So up here, somewhere in this code, you're going to have JSR, say label A. Okay. Then down somewhere here, you'll have the A, and you have lines of instruction here. And at the end, you'll have RET. So let's say that this, let me put, this is, so here's a subroutine down here. Now over here, you may have your halt, right? And you may have data down here, and the subroutine could be sort of below that, but still before your end, the end of the program. Or it could, yeah, so there's the, okay, so let's say that this is at X 3000, and this is at X 4000, and this is, say, at X 400, say 6, okay? And let's say after this is something like out or put S, right? So the subroutine is supposed to set up some character to print out, right? This is like one of the puzzle programs. So this line here is X3001. Okay, so what does this instruction do? This is the first, let's trace through what happens. This one is executing first, right? And when this is running, the PC counter equals X 3000. So what JSRA does is it sets R7 equals to PC plus 1, which equals X3001. Okay? So so that the R7 records this address. It's the next address after whatever the address is where JSR occurs, because the PC counter holds the address of the current instruction, which is in this case JSRA. But then it does something else. It sets PC equal to PC to the PC offset to the address. It sets PC to the address at which label A occurs. Well, label A is at 4000, so it's going to set your PC counter to 4000. So instead of running, after you've run JSRA, it jumps here, and the second instruction you do is this one. Okay, this is, you've entered the subroutine. So you come down here, and what does RET do? Well, its intent is to return here, but how does it do that? Well, RET, what it does is it sets the PC, the PC counter a second time. University does this to whatever's in R7. So the point is that the subroutine is not supposed to change R7. Or if it does change R7, it needs to somehow save it, use it, and then restore it, right? Because what's happening here is that what's in R7 is 3001, right? So at the end, what RET does is it puts 3001 into the PC counter. So you have 1, 2, 3, 4. That's the order. You start here, you go here, you go down here, return brings you back there. That's how it's supposed to work, right? However, there's a problem if you have one subroutine wanting to call a second subroutine. And that's the subject of one of the puzzles. So what happens if you have, well, anyway, does this make sense? Do you have any questions about, this is the basic idea behind subroutines. And for example, this program here basically loads numbers into R6, right? So the address of numbers is in R6. Then it then it has 1, 2, 3, 4, 5 subroutine calls in a row. So it's going to execute this code 5 times, right? The first one, well, this is at 3000, this is at 3001. So the R7 will contain 3002, but it'll jump down here, do all this stuff, then jump back to the second subroutine, then jump back here. And what happens for each one of these is like R6 gets encoded to 1. So it does something to these numbers. Okay, and you can see this, there's like 2 1s here for some reason. And you can see here, load R6 minus 1. So this first one is accessed via a label. Well, not via a label, it's via a register offset. Okay. So that's the design function. So you're supposed to sort of see what this, walk through this program and see what it does. Then you can run it in the LC3 simulator, and then you write your own program here that will be that does something that basically the main program should load 2 positive numbers from memory cells with labels num1 and num2 into the registers R1 and R2. Then it should call a subroutine. So the idea here is the subroutine shouldn't know about anything in the main program. So that's sort of part of the reason for the restrictions. But there has to be a communication between the subroutine and so it's going to put the answer in R0. So the subroutine has to be able to write to R0. Okay, this wasn't clear from the original directions, so this is one reason to get the revised one. The subroutine has a restriction that can only use, apart from R0, can only use freely registers R1 and R2. So you actually have 3 registers. You have R0, which you're going to leave the answer in, and R1 and 2, but you can't use 3, 4, 5, or 6. You have to somehow come up with an algorithm, and you can't use the labels in the main method. Right? You could have your own labels in the subroutine, right? But you can't like you can't get num1 or num2 in the only way you have the 2 numbers are in R1 and R2. And you don't actually need any labels, okay? So when the subroutine returns, the main program should store the product, which is the value in R0, into the memory cell product, which is following num1 and num2. So this is the idea here is that you could call this subroutine multiple times to call it multiple times. Now, there's one that makes the thing even harder is after the subroutine returns the values in registers R1 and after it returns, the values in registers R1 and R2 should be unchanged from the values in those registers before the subroutine call. So this is setting up an algorithm puzzle. You have to solve the problem of finding an algorithm using these restrictions before you start writing the assembly code. That would be hopeless. You have to sort of try to figure out an algorithm. How can you do this only using sort of 3 variables? You have a variable R1, R2. You can change R0. You can use all 3 of them, but at the end of the day, R1 and R2 have to have the same values. So that is so this is a preparation for the following fact. We're going to end up, right now we have 2 special registers, R7 and R0. R0 is used for input, output, and transfer between subroutines and main programs. That's sort of a social convention, and then R7 has this special role in subroutines and returns. However, when we come to C programming, R4, R5, R6 are also going to be special. So in general, when you write a program, you can't just freely use R4, R5, R6, R7, or R0. You only have 3 registers, R1, R2, R3, and sometimes that's not enough. So what do you do? Well, the same thing that you have if you want one subroutine to call another. Let's look and see how that works. let's say you have JSRA, and that comes down here to A, right? And inside A, you have JSRB, and then something, and then you have RET here, then you have B, and you have something here, and then RET at the end of B. Will, you have a question?
Yeah, if you JSR to if you're in a subroutine and move on to another subroutine, how would it remember the original location?
Yeah,
So,
that's the problem, isn't it?
okay.
That's what I'm trying to illustrate, is that there's a puzzle where, let's see what happens if you just do this without doing anything special, right? Let's say this is at X 3000. This is A here is at, we don't need, this is at X, say 4000. This is at, say, JSRB is at X 400, say 6, and RET is at, say, X 4 X4009. Say this is at X 5000. This is at X 5009. Okay. Right? So let's go through and see what each of these instructions does. We have 2 JSRs and 2 RETs. So the first one, let's say this is at 3000. So this one's going to do is that R7 equals X3001, the next one after this, right? And the PC counter will equal 4000. So it will start here, then do this, right?
Mm-hmm.
And then let's see, let's go back. Okay, then it will come down here and call JSRB. Well, what does JSRB do? Well, it's going to set R7 equal to X4007, right? The next one after this, and then set the PC counter equals to X4009. So then when you call here, it does, this is 3, then it's going to go do 4 here, right? I mean, oh, sorry. Yeah, no, this is incorrect. It's not 4009, it's X5000. My color coding is, try not to get out of hand. So the point is JSRB saves 4007, then jumps to 5000, right? So this is the fourth one. And then it'll go through here and do RET next. And what this RET does, well, it just blindly does PC, because all I can do is what it does is PC equals R7, which equals X4007, which is fine because it comes back over here, right? 5, 6, then it comes down here and does the second RET, right? But what this RET does, this is the crucial one, is it saves, the RET is going to set PC equals to R7. Well, what's in R7 is 4007. So it comes up here to where 6 was, runs those instructions, runs RET again. So basically what you have is you have a little infinite loop, right? Because you've erased, you want, the intent of this RET was to do this one, to have R7 here to come back here. But it fails because this JSR erased the memory there. And that's, Will, what you were obviously mentioning, right?
Yeah.
So the problem is, and also just a sense, this is not an assembly error. Remember the difference between compile time and runtime errors? You may have seen that in a Java course, right? you have runtime errors, and 2, you have compile or assembly time errors. So to have an infinite loop is not an assembly error. If you like the program in the puzzle where you have this and you put it into the LC3 online simulator, it assembles fine. So it's not an assembly time error, but it is a runtime error, right? Because what happens is it creates a logic problem. It creates the program doesn't do what you want it to do. So it's like the error occurs at runtime rather than at compile time. Okay, so that's the problem. Now in the puzzle, you had this program with the infinite loop and asked you what kind of error it was, and the second one was you were supposed to fix it. Now the way to fix this is if I want to call JSRB here, what I have to do is well, the problem is that is this line here. You're erasing the 3001, right? So what you do, the fix, is when you want to call a second subroutine, you say store R7, right? Somewhere, like you make it some, you give it the label saved R7, right? So you store it, then you call JSRB, and then once you've returned, you can then load load R7 saved R7, right? Because this one saved the initial R7. This one overwrote it, but then afterwards I load it back in. So it loads this one here. So if this was X3001 here, so you've saved it into a memory cell, then this one, the register was in the 4000s or something. Then down here, you've restored it to 3001. So when you call this return here, it goes back to PC equals X 3001. So this strategy of the strategy sort of save, use, and restore, right? You save R7, you use R7, you sort of save old R7, use new R7, restore old R7. So, and if you do this, whenever you call a subroutine, you can have subroutines within subroutines within subroutines, right? Because each time you're restoring the old one, as long as you have enough places to save, and at the end of each if you save this sort of down here, you can have stuff in your subroutine. You can have memory cells with labels in your subroutine. Okay, so that is sort of behind the story with subroutines that I wanted to tell. So you sort of get the big picture here, right? And this is what's happening with trap calls, these subroutines. This is you're right. This is just an algorithm problem. This is sort of like how you can use, and here's how your program's organized, right? Look, subroutine code with any data memory cell labels it uses following RET. So your subroutine can have its own memory cells, right? It just can't use the ones from up above. Sort of, you can use it inside. Okay, so this is this one. Now, the second thing we need to introduce is the idea of stacks. Some of you are familiar with stacks from, let's see. someone's asking, but Professor, when we run the program, it does not stop after first RET in assembly puzzle 4. Well, this is what we just talked about. The problem is that it's got an infinite loop in it, right? Simran, did we answer your question?
Professor, when like we actually run it after the address 3006, it does not move to the next step, like it's stuck there.
You're talking about,
The assembly puzzle 4.
and there's two of them, right?
Mm, the one that is, yeah, from that question, I guess. The
Yeah, we've been,
first
this
one.
is, let's see, let me puzzle 4. Yeah, this is the one, right? This is the one I talked about first. It has JSR-A, then JSR-B, so it's got a problem. So this is going to fail, right?
Yeah, so it's an assembly error, right?
No, it's not. Did this compile and run? This is what I
No,
mentioned.
so
And it's
after
okay.
the,
Let me show you. Let me show you. Let's say that I show you the difference, just so it's clear.
okay.
Copy. Then let's go to line LC, not LC3. Oh, no, it's one line. That's why it's not picking up. Online LC3 simulator. Okay. So I come in here and I paste the program in, and then I assemble. Well, it assembled, so there's no assembly errors. If there was an assembly error like this, right? Oh, you've got an error in your assembly code. That's an assembly error. You've made a syntax mistake. It's like if you wrote a Java program and you compiled it and it didn't
Can you
compile.
like
That's a compile
stab?
time. That's a compile time error or a assembly error. Okay.
Okay.
So if I do this and assembles, and then I load in the simulator, and then now it's supposed to print the number, what, 5 to the screen? But if I run it, well, let's step through, right? Okay. So it jumped here. Now you can see the PC counter is 3003. R7 is 3001, right? Okay. Then we step. Okay, R0 now was 0. Oh, we zeroed, then we step. So R0 is 5. Now, what JSRB is going to do is going to add X30, so we get the ASCII code for 5 here. So now, see, look, R7 is 3001. Now here, when I step here, okay, I've come down here to B, which is what you want. But look what R7 is now. It's 3006. Okay, so now when I step here, okay, I've got R1, I've got the X30. Then I step and I've got the ASCII code X35 for the code here, and I've got return. What return's going to do is put 3006 into the PC counter. So I step, there's the 3006, so it's stepped up here. So the next one it's going to do here is RET. What RET is going to do is put 3006 into the PC counter. So I step. Okay, it did it. It did it again. It's an infinite loop. This return statement just calls itself over and over again forever. That's why it's a runtime error. You've got a loop, an infinite
Oh,
loop.
I thought it's like the assembly error because it's like not stepping after the 3006.
Yeah, but that's not an
So,
assembly error. That's
okay.
like you wrote the wrong program. The assembly code's doing exactly what you told it to do.
Mm-hmm.
You have to think about this. RET only does PC equals R7, right? It isn't concept. You have to think at the literal level of what it does, not the conceptual level of what you thought it wanted to do, right? Originally, this RET was going to return you here, but it doesn't. So
Mm-hmm.
that's why in this puzzle, this first program fails, and this is trying to elicit why it fails. Okay.
Okay.
Now
Thank you,
this,
Professor.
okay, then this program is correcting that problem. See, because here you're supposed to store something, you call JSRB and load it. So if you put in I mean, it's obvious that you put in R7. When you put in R7 here for this, it's going to run and print the 5. So this one has no runtime errors or compile time errors, and it actually runs and perform. So that's what we were talking about up here with, so I was talking about this puzzle as what it was supposed to be doing is this was, you have the design of what you want with one routine, then you have the problem and how you solve it with this second thing here. So this is the idea. Does this is that good?
Yes, thank you,
Okay.
Professor.
Good. Well, I'm glad you asked that because I think this is like it's important to understand this as going forward. Okay, so we have the idea of a stack. It's a data structure. So you might be familiar with this if you've had CS208, which is about data structures. And what is, but you can understand what a stack is because a stack isn't dependent on a language like Java or C. It's just a way of storing data. Now, what a stack does is it stores information in a pile. That's why it's called a stack. That doesn't really, I guess, help you to understand it. Well, just think for a second of sometimes you may have gone to a restaurant where they have like some container where there's a stack of plates in here and there's a spring on the bottom, right, that pushes up. So you take the, so when the clean plates, you put in a pile of clean plates, a stack of clean plates. So, but then the whole idea of this is when one person if someone wanted to put another clean plate on, they have to put it on the top, right? Now, if someone wanted to take one off, they could take it off from the top. And so the technical term, okay, put is used for this operation of putting something on. And because this was early on, this is like the 1960s or 70s. So they used the word push because of the alliteration with P's to push it off the stack. So you take the top one off, push top one off. Now, if you just wanted to see what that one was, you could look at it to see if you wanted to push it off or not. Look at top. That's the operation peak. Again, keeping the alliteration of the P's. See, so basically, a stack is like a bottom, some memory cells, right, where you put the data, and 3 subroutines: put, push, and peak. So, like let's practice. Let's say that you had let's say that you typed letters. You first typed an A, right? And then and then what you do with the A, like a person types or enters A, okay? And then what the program does, it pushes A onto the stack. So here's a picture of the stack, right? Then the person types B, and the program response pushes B onto the stack. Well, it's going to go on top, right? Then C, she'll have C. So here's a picture of your, but let me draw it one so you can sort of see it in action. So first we're going to have A. That's the picture after the first one. After the second one, we'll have AB, and after the third one, we'll have ABC, right? So this is sort of time-wise. This is sort of like 1, 2, 3, push C, 1, 2. It's sort of the state of the stack after each instruction. Well, what happens then if we push something off the stack? The only thing we can push is the top one. So if we call push, and then we print, let's say we print it. So what the person has typed has been A, what they see on the screen is ABC, right? And the program pushes off the top and prints it. Well, after you push it off the stack, you're going to have the state of the stack will be AB, and you will have printed C. then if you push again, running out of space here, you just have the A and you'll see B. Then the last one is you push 6 and you'll see A. So here's the effect. If you push a sequence of characters, first A, first, last, and then you pop them off, right? You get this one off first. So what the slogan for a stack is last in is first out, because the last one in is the first one out, and the first one in is the last one out. Okay, now you have okay, so that you've probably experienced an unpleasant stack or more or less stack in getting on and off airplanes, right? It may be that you're one of the first ones on the plane if you're front of the plane, but the idea here is that the passengers if the idea was the most efficient thing for people getting on an airplane if they didn't have reserved seats was for the first ones on to go to the back of the plane, right? Like this. So then the people up here at the front would be the first ones off. So they'd be the last ones in and the first ones off. So this would be, I mean, that's not what people do. They have sort of more status where the first ones in are also the first ones off because they've paid more money to be in the front of the plane. But anyway, so you have those data organization issues or people organization issues. So that is what a stack is. Now, in the program, here's a program. Unfortunately, I need to put it so it's on one page. So there's 3 subroutines, okay? That has, and here's the sort of memory that you put at the bottom of your program. So you write a program that takes in from the keyboard an arbitrary string of characters and prints them in reverse order. Use the following subroutines, which should appear at the bottom of your program. So you're going to write a program that's going to use a stack. You're going to do exactly this. It does exactly this, where the user is going to type in some characters and the program's going to then print them in reverse order, okay? So let's look at the subroutine. These are sort of simplified subroutines because they don't call second subroutines, but initialization, init. Well, here we have a base. The bottom of our subroutine is going to be 4,000, okay? And we need a signal to know if it's empty, right? -1. So basically, you notice the -1 is right after the 4,000, right? So let's see what happens. The initialization routine, init, which is the first, you'd use this in your program by JSR init, right? You'd put these at the bottom after your hold, after your program data, then you could call JSR init. It would load the base into register 6. So register 6 is going to be special. It's got the base in it, okay? And it's actually going to be the top of the stack, okay? It loads empty into R0, which is the -1. So -1 is R0. Then it stores -1 into R6. So here, the picture of our stack then is we have X. Oh, let me make this always on top. Is X 4,000 has -1 in it. This is a result of init, and also R6 is equal to X 4,000. Okay, so let's say you have a routine in your main routine that takes in a character from the user that has called get C in some loop or something. What you want to do is then call push, which basically, okay, here's the interesting thing. Stacks grow upwards to lower memory, right? So if I draw this, if I, in push, I add -1 to R6. Well, R6 is 4,000. then R6 points here. It was pointing here, now it points 4,000. Then it copies what's in R0 using str into, so let's say you type the letter A, then you're going to get the ASCII code for A here, right? Then you return. So maybe you're going to have a loop that gets a character that's going to read it from the console into R0, then you call push, which puts it here, and until you have some signal that will stop the input, right? Like you have it so that you check whether you've pressed the enter key, which is return, which is the ASCII, which would be the number A, XA for, that's the ASCII code for return for from the keyboard, not this return. Okay, so then after you finish the loop of type, like maybe you have R6 here would equal X4002, and you'd have B here, you'd press enter, then you'd have another loop that would check, that would peak, right, at R6, and then, because you could then see, is it -1, right? Because you've got -1 at 4,000. So you can tell if it's empty with peak. So as long as it's not empty, what you can do is you can pop it off, which basically loads what's in R6. That's, so if R6 is the top of the stack, it would load the B into R0, and then it would add 1 to R6. So basically what would happen for pop is B would go to R0, and R6 would become X4001, the next one down. So then if you called pop again, you'd get the A into R0, and R6 would go to 4,000. And then if you peaked at the number, you'd see, oh, -1, the stack is done. So you'd exit the loop, and you would then be done, because your second loop would have popped off and then called out and then peak, and then decided whether you should branch or go to halt. Okay, so basically your stack program here is an exercise in using a stack to reverse a string. Okay, and here's the more explicit stuff of what you've done. Okay, so now there's an exercise here that's on Piazza. There's a new text, and there's also stacker size. Okay, so what you want to do, and this follows the convention, like here's a list of instructions, right? And you follow it in, like what you do is, after you label this, after this is like, you do the first instruction, then you draw the stack. You do the second instruction, put the stack here, so that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is going to show the state after all 11 instructions have run. So what you want to do is see the state, says draw the state of the stack after each operation as a stack of letters. Okay. Then 2, if the letters are printed as they pop off the stack, what is printed? That's what you're asked for in regex. Then here's the same one. You execute there's 6 instructions. So it's like a flip book, right? That you sort of, this is the state after the first, second, third, after each instruction runs, you draw the state of the stack. And that's it. This is just practice in using stacks and visualizing it, but you get credit for it on regex. Okay. I think. Not sure where that is. Let's see. I think we saw it last time. Oh, this is the the programs. Okay. We come here. Oh, you haven't seen, let's see, do we have, maybe it isn't out yet. Okay, we'll have to look at that. Because it may be that the stacks are for next week. So I'm sort of jumping the gun here with the text and showing you what you have to do. Okay. So questions?